Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, so far, we have talked about the concept of deadlocks and also the deadlock detection. Now, in this section, section 5.3, we're going to talk about dynamic deadlock avoidance. In particular, we're going to talk about an algorithm called the Banker's algorithm. Okay, so far we have talked about deadlocks, and we also use the resource allocation graph to describe the processes and the allocations of the resources for the different processes. And we introduced one algorithm called the graph reduction algorithms. We use the graph reduction algorithm to check whether the current graph is in the deadlock state. Okay. Now, one approach to dealing with the deadlocks is to allow the deadlock to occur, and then provide some ways for detection and recovery. Okay. So we try to recover from the deadlock. Okay. Now the recovery from deadlock can be accomplished by one, destroying one or more of the processes. Remember, the deadlock happens when there's some kind of circles in the resource allocations. For example, like process 1 is holding a resource, okay, and then requesting for other resource, okay, for another resource, and the other resource is held by another process. Okay, now another process cannot continue because it also requesting for resources held by this resource. So we now eventually we have some kind of circle in the resource, allocation. So none of the process can continue because you have to break the circle to break the deadlock. Okay. Now, the other way to recover from the deadlock is to remove some of the resources held by the deadlocked processes. Now, the process has been deadlocked, so we'll remove the resources. Okay. So then the deadlock process is no longer deadlock anymore. An alternative is to avoid the possibility of deadlock by delaying the acquisition of resources. For example, if with the current resource allocation graph, now if one process is requesting for additional resource, then we're going to check if we grant this acquisition, whether this is going to lead to the deadlock state. If it does, then we just delay this acquisition, saying, no, you don't, take that resource. So then we will eventually grant the acquisition, but not at this moment. So we delay the acquisition. Okay. Okay, so before we can discuss any approaches for the deadlock solution, like a deadlock avoidance, so let's first talk about the resource claim graphs. Now, resource claim graphs is very similar to the resource allocation graph. It's going to include the information like which process is actually currently requesting for which resources, and also which process has acquired which resources. In addition, the resource claim graphs also include the information like maximal claim of a process. So for each process, once it's created, the information about the maximal claim should be provided. Okay, now what is maximal claim? So maximal claim of a process is the set of all resources the process may ever request. Now, so that information should be included in the resource claim graphs, other than the information provided by the resource allocation graphs. Okay, so let's take a look at the example. Okay, so let's see, we have two processes, P1 and a P2. And we have a resource, R, which has 3 units. Okay, now initially, process 1, both process haven't make any request. So the resource allocation graph should be just like this. There's no actual request and there's no allocation. So that's it. However, in the resource claim graphs, we should include the, any potential request. For example, you say the maximum claim for process 1 is 2. Okay, for the resource. There's only one resource at this moment. So that means process 1 may potentially claim for resource. Okay, for the resource. And also it will potentially claim for 2 units of the resource. Now we use the dashed edge to represent the claim. So in this case, the maximum claim is 2, right, for process 1. And then we have maximum claim for process 2 to the resource R. Okay, so that's the resource claim graphs, even before any resource actually make a request and claim the resource. Okay, so now let's see. Suppose process 2 requests 2 units. Okay, so process 2 requests 2 units of the resource. So then this gonna actually convert. Okay, let's see. Okay, let's do the next one. So that's still the claim. So now process 2 make 2 requests. So that means that's okay because 2 is still less than 3, right? The maximum claim is 3. So it makes 2 requests. So basically we're gonna change 2 of the claim to request. Okay. And then we find out, all the 3 units are available. So then process 2 can actually acquire the resources, right? So this request will quickly becomes allocation. And process 1 is unchanged. Okay. Now, if at this moment, process 1 wants to make 2 requests for the request for 2 units of the resource. So I changed the claim, the dashed edges to the real claim. Okay, so now I have P2. I have a real allocation and 1 claim. Okay. Now what happens? Process 1 makes 2, make request for 2 units of resource. But there's only 1 unit, right, available. So then what happens is process 1 gonna be, okay, blocked. Okay, process 1 gonna be blocked. Now, since process 2 is holding 2 resources, but process 2 is not gonna, still not ready to run because there's still another potential for process 2 to acquire the third unit. So at this moment, if process 2 release one of the unit, okay, so let's say process 2 release one of the unit, okay, so let's see, and then so then it free up one of the unit, so making the available units from 1 to 2. So then process 1 at this moment can, it's unblocked. And then I can quickly change this. Let's see. Change the request. Okay. Right? I change this, request to allocation. Now, the story is going to continue because process 1 gets all the resources and the process 1 can execute and finish the job. And then later on, process 1 going to release both units of the resource. Okay. So this can actually make all 3 units free. So potentially process 2 can complete. That's a good, right? That's a good situation. Okay. So the claim graph. Now what's the difference between the allocation of claim? So the potential request edge, so that's a claim edge, may eventually be transferred into the actual request edge and subsequently into a resource allocation edge. Okay. So, but no matter what happens, the sum of all request, allocation, and the claim edge between a process and the resource will always remain constant. Okay. So if the maximum claim for process 2 is 3, so the process 2 can only make a maximal 3 actually requests. So, or you can make a 2 requests, so and 1 claim. So the maximum going to be 3, right? It doesn't matter whether these 3s are all claims or all requests or all allocation. So there's only 3 lines, between the resource and the P2. And for between the resource and the P1, there's only, only 2. Okay, either these 2 are both claims or both request or both, allocation, or just 1 request and 1 claim. So the maximum going to be maximum number of edges going to be just a 2 for process 1. For maximum edges going to be 3 for process 3. So that's a constant number. So the 2 is a constant number for 2, 3 is a constant number for process. Oh, and 2 is a constant number for process 1, and 3 is a constant number of edges for process 2. Okay, whether the edge is claim or request or allocation. Okay, so now let's introduce an algorithm, the Banks algorithm. Now the Banks algorithm emulates the strategy used by a bank when issuing loans. Now in this bank's algorithm, you can think about the customer as a process. Okay. And the loan, a loan corresponds to a resource allocation. Okay. So that's a resource. Okay. So that's a loan. Okay. And the maximum claim introduced in the previous slide basically corresponds to the credit limit of a customer. So that's a customer, which emulate the process. Loan emulate the resource. So the resource, the loan also have some kind of limitation. That's the number of units, just simulate the number of units in the resource. For example, each bank may provide a loan of 1 billion for a month. Okay. Now, if you have too many actually customers to borrow money in this month, they have to delay some of the customer. Now, for each customer, the maximum claim is the credit limit. So, for example, this particular customer have couple of claims, 1, 2, 3, 4. Suppose each claim represents 1 million. Okay, so that this customer can potentially borrow $3 million from the bank. Okay, so it can potentially get $3 million loan for buying a house, buying any business or anything like this. So the customer actually credit limit is based on the customer income and also based on the credit history. Whether this customer has a bad history or good history. If the customer is actually a good customer and never have any kind of bad history, then the bank may actually increase the credit limit. Okay, so then when a customer say, okay, I want to actually borrow $2 million, so then you're going to change to request edge or to actually claim edge, okay, the dashed edge into the request, because each represent 1 million. So I make $2 million request. And then the banker, on the other hand, are going to check whether in this month I have enough balance to grant this request. Okay. So if the resource is actually not enough, we don't have $2 million in balance, then the granting of the request should be postponed, maybe to next month, so we're going to be able to provide a loan for you. Okay, so that's basically the background for the bank's algorithm. Why we call this algorithm bank's algorithm, because it emulates the strategy used by a bank. Now here's how the bank's algorithm going to work. Okay, so now suppose one of the customers makes a request. So suppose a resource request in a state S. So it's currently, you have all these processes. Okay, let's assume this is a customer at this moment, and there's resources, different type of loans, and then you have the allocations, right? And you have a request, and you have the claim edge, and also allocation, request, claim, another claim. So you have all these information here. So this make a request for resource 1, resource 2, right? So suppose a resource request, that's the current state. A resource request in a state S, okay, is made. Now, the bank's algorithm is going to temporarily grant the request by changing the request edge to allocation edge. So let's say So this particular one, let's say, let me change the color to simulate a request. So this particular customer, and make a request. You're going to change the claim, the dashed edge, to a real claim. And then if the resource is available, then we can actually grant this claim, okay, to allocation. Okay, so we change the request edge to allocation edge. Now once it's done, that's just temporary, okay. So once this change is done, then we execute. So this, we basically change the current, the graph S to S prime, next, So then we're going to execute the graph reduction algorithm on the new state S prime. So that's the new state. Okay. Now remember the graph reduction algorithm. So we basically eliminate all the unblocked processes under their edges, right? So then this is going to free up some of the resources, and then make some of the blocked process becomes unblocked. So then we remove the unblocked processes. Now, if we can keep going this way, eventually reduce the graph. So if the graph of state Si, so like this state Si, is completely reducible, so that means we can eventually eliminate all the processes, then we accept this request and change the request to allocation. Now this becomes the new state. Okay. Now if the graph S prime is not reducible, then we disallow the acquisition by reverting to state S. We just revert back to state S. So we just eliminate that, allocation and change it back to the claim. Okay, so that's the Banks algorithm. Okay, so let's take a look at an example of Banks algorithm. Now here we have a resource claim graph. Okay, so in this graph there are three processes, P1, P2, and P3, and the two resources, R1 and R2. So you can see this diagram, three processes and two resources, right? Now initially resource 1 has 2 units. You can see 2 circles inside R1 and 3 circles inside R2. So R2 has 3 units. Now the resource allocations and also the claims are shown as in the graph and the table. That's the claim graph, resource claim graphs. Okay. Now, so in this graph, you can see that process 1 has a maximum of 2 claims for R1 and a maximum 1 claim for R2. And the process has 2 claims for R1, 2 claims for R2. Process 3 has 2 claims for R1 and a 2 claims for R2. And then this diagram, the claims diagram, the claim graph also shows the current allocation. P1 has no allocation for R1, but there's 1 allocation for R2, right? That's the allocation for R2. Okay, and the P2 has no allocation. You can see P2 has only the request and the claim. P3 has 2 allocations, right? For R2. Okay, it's for R2. Now the request looks like each process has 1 request for R1. So process 1 has 1 request for R1. Process 2 has 1 request for R1. Process 3 has 1 request for R1. Now, none of process request for R2. Okay. So, however, the potential requests, it's basically the maximum claims we have. So P1 has a potential request for 2. Right now, it's there's no, so the potential request for R1 is 2. Okay, even though there's currently 1 request, but the potential could be 2. And P2 also has a potential request for 2. P3 also have a potential request for 2. This matches that number. Okay. And P2 has potential request for 2 for R2. P2. Yeah. So far there's both of these are just a claim. Now here's the availability. Available units for each resource. R1 right now has 2 units available. Even though there's a claim, but it hasn't been allocated yet, so there are 2 available. And for R2, there are 3 units, but 1 unit is allocated to P1, 2 units are allocated to P3, so there's nothing left. Okay, so that's the current state. Okay, so here we have a resource claim graph, right? And we should use the bank's algorithm to check which request we should grant. Now currently, all 3 processes are requesting for 1 unit of R1. Now which request should be granted? We can actually check each individual one, and we only grant the one that will not lead to the deadlock. So now first, we assume that the request by P2 for 1 unit of R1. So request of P2 for 1 unit of R1, that request is tentatively granted. Okay, so we're supposed to grant this request. So the request becomes allocation. Okay, so now 1 unit of R1 is allocated. Now this is going to change the diagram from the current diagram S to S prime. Now we're going to check whether S prime is in the deadlock state. If it is, we're going to revert. Okay, so that change, the grant of this acquisition, will lead to the change of this table. Now let's check what data has been changed. Now first, the available units, R1 has 2, R2 has 0, but after we grant this acquisition, so now only 1 unit of resource 1, R1 is available, right? So only 1 is available. What else has been changed? Okay, so these are actually the maximum claim. So P1 can claim up to 2 units of R1. P2 can claim up to 2 units of R1. P3 can claim up to 2 units of R1. And P1 can claim 1 unit of R2. P2 can claim 2 units of R2. And P3 can claim 2 units of R2. So that's the current allocation. Okay, so you know that this one is allocated, right? So we know that. Now, what change are you going to make if we change this request to allocation? So initially P2 is requesting for the resource 1, right? So that's a request. Now this change going to eliminate the request from 1 to 0. So there's no request anymore. Okay. Now there's still a claim, but that's not request. Now also the current allocation for R1 initially 0, that changed to 1, right? So we change this 1 to 0, change this 0 to 1. And also, the potential requests, since already 1 has been allocated, so there's a 1 request, 1 claim, so potentially there are 2, right? But now this is going to change this to 1. Okay, so that's the potential requests. Now what we can do using the bank's algorithm, using Banks' algorithm, we're going to check for each process. Now with the current condition, with the current graph S prime, so that's the current situation. Okay, so we need to check each of the individual process to see whether the potential request for each process gonna meet the, potentially, so gonna be satisfied. So that means whether the available units right now can meet the needs of the potential requests. So now let's say for P1, so then the potential request is actually 2 for R1, 0 for R2. Now, what's the available unit for R1? There's only 1, but the P1 potential need actually 2. So that means the potential request, has more than the available unit. So that means P1 is blocked. There's no way that the P1 gonna actually get all the resources it needs. So let's see, I'm gonna change this P1 to blocked. I use red color. Now let's check the P2. Now P2 used to have 2 potential and 2 unit, and the available units were 2, 2. So in this case, P2 will be blocked for sure, right? Because potentially P2 needs 1 unit of R1, and there's 1 unit of R1. That's okay. But P2 also potentially needs 2 units of R2, but there's no actually unit of R2 available. So P2 is definitely blocked. Now what about P3? Okay. Now P3, so it has, potentially request for 2. For R1, there's a potential for 2, but there's only 1 available. So P3 is also blocked. Now all 3 processes are blocked because the potential requests actually, for each process, is more than the available units. So the current available units cannot satisfy all the processes. Now that's not good. So therefore, the request by P2 is denied, and the tentative state reverts to the previous state. So okay, so let's revert back to S. So the case 1, the request will be denied. So now let's look at the case 2. Remember, in case 1, we tentatively grant the request of P2 for 1 unit of R1, right? We grant this one, and we actually change this to the allocation, and then we find out this actually leads to the deadlock state. So we actually denied this. And now let's try another case, case 2. So let's say we actually, this time we grant P1. So if P1's request for 1 unit of R1 is granted, that's this one. Now suppose this request for R1 is granted. So now we say if it's granted, then we change the request to allocation. Now that change also going to change the resource claim graph. The resource claim graph, now this time the S prime is this. Okay, S prime is this. Now this is also going to change the tables here. Okay, so again, one of the units for R1 is gone. So the available units for R1 is switched from 2 to 1, right? Now what else is changed? So now this time we change the P1. So P1, initially there's no allocation. Now this time, because the allocation, the request for R1 has been granted, So the allocation actually switched from 0 to 1, right? There's one allocation. And the current request, that request has been switched to a allocation. So the current request, number of requests is 0. Okay. And also the potential request for our P1. So, the maximum claim is 2. Now 1 is granted. So the potential going to be dropped to 1. Okay. So that's a change. There's no change for P2 and the P3, right? Nothing changed. Only change this one. Now let's see. Once we grant the request for P1's request, now what happens? Can we continue? Let's see. So let's check the potential request for each of the processes. Now process 1 will potentially request for 1 unit of R1 and 0 unit for R2. And then that's exactly match the available units. So that means there's a, it's possible that we can, P1 can continue. Oh, sorry, I just put the wrong, So yeah. So P1 should be okay. So the potential requests is 1 for R1, 0 for R2. So that's gonna meet the matches the potential actual available units. Okay. Now what about P2? P2 actually potential request for 2, but there's only 1, right? So P2 will not be granted. So P2 will be blocked. P3, potential request for R1 is 2. Now we only have R1, 1 unit for R1. So that will be blocked. P3 will be blocked. Okay. But the P1 will be granted. Okay, so P1 should be okay. So this not going to lead to the deadlock state. So we just actually the potential request for P1 may be satisfied, and thus P1 is not blocked. So we grant this, acquisition. Okay, so that means in case 2, when we grant P1 with 1 unit of resource 1, it will not lead to the deadlock state. So we actually move the whole resource claim graph to the next state. So here's the one we can actually move to. So we have P1, P2, P3. So then we have a resource 1 and a resource 2. Resource 1 has 2 units, resource 2 has 3 units. And 2 units of R2 are allocated to P3, and P1 has 1 claim. P1 has a request, and then we granted a request, so it changed to allocation, and we find out after we allocate 1 unit of R1 to P1, this is not going to lead to the deadlock state, so we just change to that state. And then we have a 1 claim from P2, 1 request from P2, and we have 1 allocation to P1, and we have 2 requests, 2 claim for R2. I think that's, we have 1 claim from P3 and 1 request from P3. Okay, So now that's the new state, and we accepted this because we use the bank's algorithm, and we find out change this request, change the request of P1 to R1 were not needed to the deadlock state. Okay, so in that case, we also change the corresponding data, right? Because the resource for R1 is changed back to 1, and for P1, the current allocation, it was 0 for R1, but now it's 1. The current request for R1 is changed to 0, and the potential for R1 is 1 because P1 already acquires resource 1 unit of R1, so there's potentially only 1 more request. Okay, so that's a new state. Now, with that new state, it's possible that we can actually complete the whole executions of these processes, because so we know that with that new state, now P1 can potentially complete the job, because the potential request for P1 is 1 for R1, 0 for R2, and then we exactly have 1 unit for R1 and a 0 unit for R2. So P1 can potentially finish. Now, if the second claim for P1 changed to request, and eventually that request is granted, now we find out P1 gets all the resources it needs. So now P1 can complete the job and P1 can quit. Okay. Now let's assume P1 just complete the job. Okay. Now we can remove the P1. P1 is quit. Okay. It will also remove the edges that are connected to the P1. Okay, so we complete this. Now, once we complete this, so because P1 is holding 1 unit of each resources, once we remove this P1, then we free up 1 unit for R1, we free up 1 unit for R2. Okay, so that means the unit for R1 was switched back to 2. Again, the unit for R2 will be changed from 0 to 1. Okay, so let's rewrite this. So in this new state, once we eliminate P1, so we eliminate P1. Okay, we free up some unit of R1 and 1 unit of R1 and 1 unit of R2. Now, let's check the remaining processes, P2 and P3. So P2 can have a potential 2 requests for R1. That's okay. And 2 requests for R2. Now this is not going to be satisfied, right? So it looks like even with P1 process 1 removed, we still cannot complete the P1. So that means P1 is still going to be blocked. Or P2 is still going to be blocked. Okay. Now what about P3? Now P3 has 2 potential requests for R1 and a 0 potential request for R2. So now we have 2 available units for R1 and 1 available unit for R2. So that's good news, right? So then we can basically satisfy P3 if P3 wants to complete, which means if all the request and the claim for P3 eventually switch to allocation, then P3 gets all the resources. Now, if P3 gets all the resources, then you can remove P3, right? And all the edges. Now, once we remove the P3 and the edges, now let's see what's left. Okay, so let's see. So if P3 is removed, so you're gonna free up the 2 units of resource for R2 and free up additional 2 units for R2, or 2 units for R1, additional 2 units for R2. So you're gonna have 2 units for R1 and 3 units for R2. So now we have a P3, we have a maximum claim for 2 and 2. The kind of allocation is 0, 2, 1, 0, and 2, 0. Now we have enough resources for the potential request for P3. So P3 can finish. Okay. So now let's see if P3 is removed, then we have only P2 left. Okay. And also okay. That's fine, right? P2 has enough resources available, so P2 can finish at any time. So then we can complete all the processes. That's good. Okay. Okay, so the Banks algorithm can be simplified if all the resources each has only one single unit. Okay. Now with single unit of resources, a process P can be blocked only if P is waiting for a resource held by another blocked process P prime. Now, since P prime is blocked, so P prime must be waiting for another resource held by yet another process P double prime. So you can keep going this, and so eventually to make a chain irreducible in the claim graph, in the resource claim graph, the process must be blocked in the directed circle. Okay. So now the Banks algorithm can be simplified as following. So again, given a request for a resource in a state S. So currently, there's a resource claim graph. And then we temporarily grant the request by changing the request edge to the allocation edge. So we particularly for P, if the P, we grant the request of P to a resource to allocation. Okay, from request to allocation. Now then we start with the requesting process P and determine if the graph in the temporary states S prime contains a directed circle. Okay, if there's no circle, then accept the S prime as a new state. Now if there's a circle, that means there's a deadlock, and then we just revert to the previous state S. So now let's take a look at this example. Now here we have 4 processes, P1, P2, P3, P4, and 3 resources, R1, R2, and R3. Each has only 1 unit. Now there are two outstanding requests. P1 is requesting for R1, R2, and P3 is requesting for R2. So now let's see if we grant P1's request for R2. So now this request becomes the allocation. Now what happens? Okay. Now here, since this is only one unit for each resource, so all we need to check, we can start from P1 to check whether there's a circle, there's a loop. So now we actually have a closed circle. P1 will potentially claim for R1, and R1 is currently held by P3, and P3 is requesting for R2, and R2 is currently allocated to P1. So there's a circle here. So we have a closed circle. So there's a potential for deadlock in this case. So we will actually deny the acquisition. Okay, so this acquisition will be denied. So let's take a look at another situation, another case. Okay, now let's remove this. Okay, now suppose P3's acquisition for R2 is granted. So now we have this. Now we have the kind of loop, a circle. So you have going from here to here, P1 also going from here to here. So there's no circle. So, okay, so then we're gonna, accept these acquisition. So this is gonna be the one. Okay, so this is gonna be the new state. It's pretty simple, right? For if the resources has only one unit, all the resources each has only one unit. Now if in the case number 4, if the clan graph looks like this, so we actually P1 and P2 did not need R2 and R3 respectively. So that means P1 doesn't claim for R2, and P2 and doesn't claim for R3. We don't have this one. Then this, okay, so this clan graph will be okay. There will be no deadlock situation. Why? Because there's no loop. Now this is disconnected. This is also disconnected, right? So this potentially there's no loop. So there's no way you can create a loop. Okay, so that should be okay. Thank you.